We continue with the study of inductor basics, part 2. So, we have seen that the relationship between the voltage and current across an inductor is given by this relation here. V of t is equal to L into di by dt. The voltage across an inductor is proportional to the rate of change of current through it, and the constant of proportionality is what is called inductance L, and L is measured in henries. So now we look at some examples. So in this case, suppose a current I of t is forced through an inductor, and the current profile looks like this. So it remains constant to I naught for a period till t naught, and then makes a sharp jump, and the current becomes equal to I1 at t is equal to t0. So we now know that if you want to, if such a current is pushed through an inductor, how the inductor will behave. So we know that the voltage across an inductor is equal to the proportional to the rate of change of this current. So initially, if this current has been I naught for a long time, like this, then there is no change of the current with respect to time, and the voltage remains 0 for a period till t naught. Then at t naught there is a sharp jump, and if this time of this jump is very small, it means, in other words, that the slope of this change is very large. There is a fast change of the current, which means that the derivative of this transition is very large, and in ideal condition infinite. This will result in a large spike across of voltage across the inductor. So in this case, a large voltage will develop across the inductor, and in a practical situation where if you are able to force a current structure like this, it will most likely result in a discharge. But in the idealized conditions shown here, this sharp current will then, this sharp voltage will then come back to 0 because the current remains constant after that. So it again remains, behaves like in a DC condition. There is no voltage across the inductor. So this was some transient behavior in static cases, or where there were some transitions. Now we look at how does it behave to an sinusoidal signal and or an AC response. So in this case, the current is again forced through an inductor, but the current profile is given by A into sine of omega naught t, where omega naught is 2 pi f naught. So this is basically a sinusoidal signal which has a period of, the time period t naught is equal to 1 by f naught. If we apply the equation v of t is equal to L into d of I by dt, we get this expression. So this is the voltage developed across the inductor. So if the current was A sine omega naught t, then the voltage developed across the inductor is A times omega L cos of omega naught t. We get some insight if you look into how this waveform looks like. So this current AT I of t is equal to A times sine of omega naught t is sketched here. On the x-axis is time, and on this axis is the current in, say, in amperes. And in the bottom plot, voltage across this inductor omega L A times cos omega naught t is also sketched. So the amplitude in this case here, if this amplitude is A, and time period is 2 pi by omega naught. If you look at the voltage response, the amplitude of the voltage is omega L times A, and the time period remains the same. But the thing to note here is that the voltage response has shifted. Instead of a sine signal, we have a cos signal. An interesting thing to see here is that if you look at the relation between the voltage and the current, there's a current I of t seems to lag behind V of t. So what this means is that the voltage here, when it is at peak, the current is at 0, and then this current reaches a peak after a certain time. Then when the voltage falls to 0 here, like this, the current also falls to 0 but with a delay. Then voltage goes to the negative peak, and after that certain delay, the current also goes to a negative peak. So there's a delay of the current with respect to the voltage, and that's what is called that the current is lagging with respect to the voltage. And in terms of value, what you would see that the current lags by, in terms of phase, 90 degrees. So if you look at these sine waves, this is if this x-axis was a phase of a sinusoidal signal, so this angle here, this would be pi by 2, where cos becomes 0 and sine is at peak. So the current lags by pi by 2, and that's what this relation between sine to omega naught t shows, that the current lags behind voltage by 90 degree. So there are two things here which is worth noting, that what is defined as reactance of an inductor. So we'll see maybe about this in a more detail later, but what is defined as say the absolute value of reactance in this case is similar to how the resistance is defined as the ratio of voltage and current. If we define it in this case, the absolute value of the parameter which is defined as reactance is similar to the ratio of voltage and the current, and in this case it's omega L. So that's the what is called the reactance of a inductor. It measures what's the impedance that it shows to a voltage that is applied. So at DC, the reactance is 0 because omega is equal to 0, which in a way means that inductor behaves like a short. At a very high frequency, omega L is also very high, and inductor behaves like a open.